It's me, I'm back. More notes. Okay, so a long time ago, when we first started this whole motion unit back, when we started talking about acceleration and velocity, I had a disclaimer about how when we look at acceleration near the surface of the Earth, that in our small little world, we are going to look at it from our point of view, which means we're close to the surface, gravity pulls down, and that's how that works. But the reality is, we have to look at it from a big picture, and today is that day. So there's a universal gravitation law. This law basically says that it's not just things dropping towards the Earth. It's that the two things are actually attracting each other, kind of like magnets attract. We know this because we see things from space that get attracted to the planets all the time. So Newton, not only does he have his three laws, but he's also got the universal gravitation law, which is looking at it from a whole different perspective. Basically said that there's a force between any two masses. The force depends on the mass and the distance. So the farther apart things are, the weaker the force, the closer the stronger, and the bigger the objects. So because Earth is big, everything we have around it is small. So when they attract each other, you don't actually see the Earth move because it's too massive. We see the small things around the Earth. So here's a picture of a planet. It could be the Earth. Every time you see an object, imagine you went to the moon and you had a telescope and you watched things at the Earth. Every time something came near the Earth, it would pull towards the Earth. It would pull towards the Earth. Doesn't matter where you went, you could watch. Could be dust from the atmosphere coming down, it could be somebody dropping something, it could be a coconut falling off a tree. No matter what, everything near the planet pulls towards it. And so when we draw a picture of what happens to everything that is near that we test, think of dropping a coconut like a small test object near the Earth. We watch it, it always goes towards it. Technically, we know they actually attract each other, but because the planet is so big next to anything we could drop, the planet doesn't appear to move. Only the small objects do. So these lines that I just drew that represented how we would test, like if you wanted to test gravity, just throw a pencil in the air. It's going to go down towards the planet. We're no longer going to say just down, we're going to say towards the planet. These lines that I drew that show how we test the field, the gravitational field, are called lines of force, and the picture they make are what we call the shape of the field. In this case is the gravitational field. We have two other kinds of fields we do this year. One is electrostatic and then magnetic. But in this case, gravity only attracts. Okay, Newton's universal gravitation law is this. Force, in general, which is still going to be in Newton's, is the attraction between two masses over the distance between them squared. Sometimes in books you'll see them use an R. They like to use R, but we use D. Continuing, so what's this big G? Well, there was a guy that was working, I don't know if he was working with Newton, but his name was Cavendish, and he was able to set up a little experiment with some very massive, small objects, and actually see them attract to each other. Excuse me. And he found that Newton's relationship of mass times the mass divided by the distance squared was proportional to the force, but it was not equal. And they came up with a constant that made the formula work. You can look up Cavendish if you'd like. So big G, as I call it, which is always used a capital letter, is the value of 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. That just makes the unit work out. But this is a big number. And so looking at forces from the, oh, I dropped an apple on the Earth, so it went down, to the, oh, objects get attracted towards each other, is a little bit about what this next example is. So we're going to use all of Newton's laws to show how much force is between a 1 kilogram mass and the Earth. So there's some information that you need to know. Okay, we're going to kind of like do this as like two little areas. The first is when we are on the surface of the Earth, our force of something, we just call it mg. But when we're looking at this from a more international universal, we know F equals big G m1 m2 over d squared. So one of these masses is the 1 kilogram, the other one is the Earth. In this case, when we drop things, we don't consider the Earth because it's already there. We just use the small mass, that's the 1 kilogram. So this side's easy. FW equals 1 times negative 9.8. Well, here's the thing. When we're comparing on the Earth, I drop things down, and then looking at it from space, we don't actually care about the direction so much. That negative is the direction, so I'm not really going to care about the negative. This is going to be 9.8 newtons. Duh. We're going to take away the negative now because the direction isn't as important. On this side over here, you need to know some things. Well, for example, what's the mass of the Earth? If you look it up, it's roughly 5.98 times 10 to the 24th kilogram. That's a 4. I also have the 1 kilogram, and I need to know the distance. Well, think about Earth. If something is sitting on the surface of the Earth, how far apart are the two objects? They are 1 Earth radius apart. Well, that means that the distance here is 1 Earth radius, or if you look it up, it's approximately 6.378 times 10 to the 6th meters. Some people round off to 6.4, just saying. So using that information, let's see if both of Newton's laws work for the same two objects. This is a 1 kilogram mass on Earth. This is our on Earth calculation. This is a 1 kilogram mass on the surface of the Earth, which means it's 1 Earth radius away from the center of the Earth. So F equals 6.67, which is 10 to the negative 11th, that's the G, times 1, that's the 1 kilogram, times 5.98 times 10 to the 24, all over this 6.378 times 10 to the 6. This takes a little while to type in, and let's see what we get. Okay, so this should work anywhere in the universe. This only works when you're on the surface of the Earth. If I was on the surface of Jupiter, I'd have to go look up Jupiter's gravity. If I was on Mars or the moon, it would have to be different. But this, I would, have to know the mass of it and how big it is. Same idea. All right, so let's type this bad boy in. I'll move this up a little bit so you get a little less. All right, so clear. 6.67 negative 11 times 1, duh, times. Why am I putting everything in parentheses? Because it's going to work out better. 5.98 exponent, and that's a 24. Now, I tend to hit enter, and then I go and divide. Okay, dividing by parentheses 6.378 exponent 6. Oops, what did I do there? I wanted second EE 6 squared equals. Well, look at that. Shouldn't the weight of a 1 kilogram object be the same no matter which one we do? It comes out, okay, so it comes out to 9.81. These should match. It's the same thing. This is good if you're on the surface of the planet. This is good anywhere in the universe. Anywhere in the universe. All right. Second example. This is a more straightforward. It says find the force of attraction between two masses of 30 kilograms whose centers. And we have to be careful about this whole centers, because if you're from the surface or the center, it can make a difference if it's a big distance. So we're going to still use F equals big G M1 M2 over D squared. Both masses are the same, so let's put it in 6.67, it's 10 to the negative 11th. How can I get away with writing 30 squared? Well, they're the same, and 30 times 30 is 30 squared. And they are separated by 0.1 meter. All right, let's just do it with me. Let's clear it, move it over a little bit. All right, 6.67, the exponent is negative 11. All right, times 30 squared, I'm just gonna put it in the parentheses, equals, and then I'm gonna divide that by 0.1 squared. And I get basically 6 times 10 to the negative 6 newtons. And that's a really, really small amount of force. Okay, 30 kilograms is like, I don't know, 66 pounds, so it's not terribly, it'd be like two small kids right next to each other, being 10, that's like 10 centimeters apart. All right, so the next part of the notes is literally just on blank paper. So I'm just gonna turn this over and use, maybe I'll use this one. This one's a little cleaner. So we need to look at this in a little separate, different situation. So here is my planet. And we know that when things sit on the surface of the planet, we are at 1 radius from the center of the planet. Make that a 1. As we send things into space, and go out further and further, we know that gravity gets weaker. The gravitational field of our planet gets weaker the farther you go away. It never technically goes to 0. It approaches infinity. Those of you in calculus can talk about the limits. If I weigh a certain amount on the Earth, let's just say in newtons, because, you know, we converted our weights into newtons, so we know. Let's just say on the surface of the Earth, you weighed 1,000 newtons. Your weight would go down as you were to go if we sent you into space, but it doesn't go down the way you would think. So let's call this twice the radius of the Earth. This is 3 times the radius of the Earth, and this would be quadruple the radius of the Earth, or 4 times. Now, think about this. I'm measuring from the center of the Earth is 1, the center out here is 2. Sometimes people start here and they call that 0, and then they call this 1. So depends if I'm measuring from the center of the object or if I'm measuring from the surface of the planet. It can be a little bit tricky. We're going to stick to the centers for right now. So I could do the whole big formula, right? I could say 1,000 equals big G, mass of this object, the mass of the Earth, over this distance squared, which would be 6.4 times 10 to the 6th squared. If I went to the next spot, I would have to do the same thing. I would say big G, mass of the object, mass of the Earth, and instead of this, I would double it. So just for fun, let's see what's 6.4 second exponent 6 times 2 equals. Well, that's going to be 1.28. Let's see, 1, 2, 3, 4, 5, 6, 7. It's going to be 1.2 times 10 to the 7th squared. And then I'm going to keep going. So there's a shortcut, okay? I'm going to call this the 111. When I want to look at what happens when I change things, I only really want to look at what happens that's different. So really, this was big G, mass of the object, mass of the Earth, over 1 radius squared. This is really over 2 radius squared. So the only thing that's different is the 2, and I should put that in parentheses. When I go to the third one, it's G m0 m Earth over 3 radius squared. And if I keep going all the way out here, it's G, mass of the object, mass of the Earth, over 4r squared. So really, at 1,000, at 1r, when I go to this, it's the same answer as what I would have gotten here, except instead of having 1r squared, which is just 1r squared, I'm going to have 4r squared. So everything is the same except for the 4. And where's the 4 lie? On the bottom. What happens when I go here? Everything is the same except this is going to be 9r squared. So the 1 is going to be on top and the 9. So when I compare this, because this would be just 1 over 1, and if I did this one, guess what it would be? 1 over 16. So the way this works, so we don't have to do all of this math, is if I know 1 Earth radius is 1,000, I'm going to see that 2 Earth radius is going to be 1/4 of 1,000. 3 Earth radius is going to be 1/9 of 1,000. And this will be 1/16 of 1,000, and so on and so on. So you can see how we'll never really get to 0. So let's just see what these numbers would be. So let's take 1,000 divided, oops, I don't want that. Clear. 1,000 divided by 4. So as I was out into space, I would weigh 250 newtons. If I went out 3 Earth radius, I would be dividing by 9. So I'm down to about 111 newtons. I'm just rounding for this purpose. And then if I do the last one, divided by 16, I'm down to about 63 newtons. So as you move away from the planet, or as any objects get further and further apart, if I double the distance, you see I don't cut the force in half, I cut it in quarters. If I triple the distance, it's 1/9. If you were to, and I'm not very good at this, let me freehand it. If I were to graph this, and this was 1 radius, 2 radius, 3 radius, 4 radius, and let's just say up here, let's see, that's 1,000. Halfway would be 500, half of that would be 250, half of that would be 125, right? We could keep going half and half. So at 1 radius, I'd be at 1,000. At 2 radius, I'm all the way down to 250. At 3 radius, I'm actually less than that, 125, and at 63, I'm even half of that. So what you see, what kind of graph do you guys call this? Okay, that's a little crappy. Okay, a lot of us remember it as exponential decay graph. So will this ever reach 0? No. This is why when they're on space stations and international space station, they will always say they're in microgravity and they are not in zero gravity, because it never actually equals 0, but it gets so small that you can't see it or you can't feel it. All right, so this is a little shortcut. If you know that two objects' distances are doubled, you know that the force will go down by 1/4. If it's tripled, it'll go by 1/9, etc. All right, that is it for now. You guys are going to do some practice with this. Thanks, everybody.